Welcome, everyone. Welcome back. Today's MCA 2025 prize winner lecturer is a Spaniard from Madrid who has been, well, maybe we could say blowing up, imploding, and otherwise cutting the waves of fluid dynamics, both with computer-assisted and natural human mathematics. Ever since his PhD from Universidad Autónoma de Madrid in 2013. With appointments at Princeton, Universitat de Barcelona, and now as an associate professor at Brown University. Our speaker and his collaborators have been making advancements on the notorious Navier-Stokes problem and its brethren, extracting insights from cultivated neural networks. It is a pleasure to introduce Javier Gómez Serrano to speak on modern mathematics at the intersection of machine learning and old mathematics.
Thank you. Okay, so yeah, thanks a lot for the introduction, and thank you everybody to be here with me in this prize lecture on what I called modern mathematics for the lack of a better name, at the intersection between traditional mathematics, machine learning, and new technologies that may appear in the near future. So first of all, getting this award is really an honor for me, but the credit should go to all of my collaborators who are highlighted here. In bold, the younger people, which I owe a lot, and maybe in the job market for future years. So if you really want to hire extremely good people, take a look at their names, and I'm sure that they will be doing like fantastic work in the upcoming future. So yeah, my talk is going to be a bit speculative. So usually there are two types of talks when you go to machine learning and mathematics, or AI and mathematics. Depending on which audience and depending which presenter you listen to, this is somewhat the picture that is depicted, especially in some media. Like, okay, AI is taking over, mathematicians will lose their jobs, what are we going to do? Is there any place in the world for us? Is it over? Do we have to sort of like give up and just let the machines take over? So my vision is not so pessimistic. I think it's not going to be over in 5 years or in any amount of years by any means. But I do think that the world of mathematics is going to change. And it's going to change hopefully for the better. I think AI and modern technologies are going to allow us to come up with deeper questions, to come up with harder problems. So I think AI is coming to stay, but it will be some kind of tool. We'll see if it is to do good or to do bad, but I think it's going to be, or my vision for AI is to be part of the world of mathematics, but as a tool. So think of it as, the way I think of it is like the computer revolution or the internet revolution, where it really, or even LaTeX. LaTeX is a very good example of something that entered the world of mathematics, stayed, and kind of made our life easy. So I think AI is going to play sort of a somewhat similar role, but we'll see. Hopefully you'll tell me 5 years from now. So this is the real takeaway message. I want to talk and I want to stress that machine learning methods are powerful and can lead to new discoveries broadly in the world of mathematics. And I'll be more specific later on. Large language models, LLMs, seem to be working well generically. Let's say untrained large language models, not dedicated necessarily to mathematics, seem to be like a good, broad overall tool that we could use in the near future. For dedicated tasks, for concrete problems, very specific, possibly small models could work better. And this will affect, I will give examples, concrete examples in the world of PDE. So in the world of PDE, one can use these small models to find instances of solutions that satisfy certain properties, even under bad conditions. And the good news, and at the same time, the bad news, is that we know extremely little. There's a lot of things that we definitely don't know in this sort of broad new area. So plenty of room to explore. Everything mostly uncharted. But at the same time, things move really, really fast, way faster than the regular mathematics sort of timelines. And here's one example. So I'm going to be talking first about breadth, then I will talk about depth. So this is, and again, dates are extremely important here, a paper in Nature, January 2024, with a model claiming that essentially IMO stands for International Mathematical Olympiad. The geometry problems from the Olympiad are quote unquote solved, not all of them, but let's say a large amount of them. This is 2024. Then July 2024, this is a blog post coming from DeepMind, where they claim that they produced a model that not just could solve geometry problems, but essentially every problem in every field was solved to the level of AI attaining silver medal level. Okay, again, this is 6 months between one post and the next one. There are caveats here. I'm not going to enter into the technical details of these claims. Last Saturday, OpenAI claimed that the IMO 2025, their model can achieve gold medal performance. So 1 year after the silver medal, there's a claim from OpenAI that they can achieve. DeepMind, last Monday, this is the New York Times, they can also achieve gold medal performance. Okay? So this is just a feeling, a small taste of how extremely fast these sort of models evolve and how technology evolves and how, how things move broadly. Now, the natural question here is, okay, what about like real, let's say real mathematics? No Olympiads, let's say professional or research level mathematics. Is this really going to have an impact? These kind of technologies, are they going to have an impact there, or is this just going to be plateauing at the level of Olympiad level mathematics? Okay, so this is now May 2025. This is a product from the DeepMind family called AlphaEvolve. I am involved in this project together with Terry Tao and a bunch of Google engineers. And this is another model that now is working in the broad domain of real-world mathematics, let's say research-level mathematics. So we released a white paper sort of explaining, and this has implications beyond mathematics. There are outputs of this product that have less to do with mathematics. I'm going to be focusing on explaining what goes on in the math direction. So how does it work first? Then I will explain sort of what it is useful for. So this builds upon a previous project of DeepMind. Again, dates are important. So this is a project or a product that was released in 2024. And the way this works is that this is going to be based on an LLM, but the output of the LLM is not going to be a natural language prompt, but just a piece of code. Okay, so there will be a query into the LLM, and the LLM is going to be outputting a piece of code, maybe several pieces of code that are going to try to solve the given problem. So the human, let's say in this case, is going to provide something called an evaluator function, which is going to score how good that piece of code is. For example, if it solves the problem very badly, then it will get a low score. And if it solves the problem very well, it will get a good score. Or if it takes a very long time, then it may get penalized. And if it does the job fast, then it may get like some kind of bonus. So based on that scoring function, the LLM is going to mutate the code and generate variations. So by doing that, it will generate new ideas that the good ones are going to be incorporated further into the code, and this process is going to be repeated through several generations. The mental model to think about this is if you sort of put 100 people in a room, you tell them, oh, look, I would like to solve this problem. You can communicate with each other. I will lock the room, come back whenever you're done. And then people will sort of interact with each other. They will discuss ideas. Eventually, one idea will be generated. This will be propagated throughout the room, and it will be incorporated in the further line of thought of the group until eventually this solves the problem or gives an answer. Now, in mathematical terms, this model or this product can be sort of seen in the following way. So one could see this as an extremizer of non-trivial functions, f of x. X doesn't need to be a point. X could be a function. X could be a group, where typically x lives in a high-dimensional parameter space, and f is, say, non-trivial. And this sort of new optimization model can outperform more traditional optimization algorithms. This is sort of what we found experimentally. So what we did was to feed the model over 50 open problems in very broad areas of mathematics, including analysis, like autocorrelation inequalities, packing problems, kissing numbers, so combinatorics, geometry, like a very broad set of problems. And what surprised us was the performance. So in 75%, it was able to match the best human construction, which may or may not be the optimal. I mean, all of these are open problems, so we don't know. In 20% of the cases, it did improve the best human performance up to date. And 5%, it was not able to do better than, let's say, humans. So 95% of the cases for these 50 selected problems was either equaling or outperforming the best human construction. There is no risk for contamination because it was really, in the cases of outperforming, this was not there on the internet or in anybody's mind for that matter. So one good thing about this sort of model is that every problem took typically a day or 2 days. So I'm not claiming that humans can get this bound. What I'm claiming is that it would take for a non-expert in these fields a lot more time than one afternoon to set it up and one night to run it overnight. If you're sort of concerned about the computational cost, or let's say even the US dollar cost, for the majority of these results, the cost in US dollars is about $1. There are exceptions, but for the majority of these results, this can really be obtained with a minimal amount of resources. And we hope, I mean, we are writing a paper, and we hope to report on this list of 50 plus a few more in the upcoming months. Okay? So this is one direction where AI and LLMs are going, which is pretty broad. I'm not claiming that this will solve every single problem in mathematics, but it would be a nice tool or a nice assistant to have, let's say, for me, whenever I work on a new problem, can I use this thing to sort of get me up to speed faster or try a bunch of like natural strategies that I would think, all within one day. So this is the sort of vision that I have for this model or presumably subsequent variations of this kind of stuff. Okay, so this is one direction where AI can interact with mathematics in the long run. Let me talk now about deeper problems. So deeper constructions to solve a much more restricted set of problems coming mostly from the range of PDE. Okay, so this is the target here is going to be very deep. It's going to be solving one single problem or maybe a small family of problems. And at the same time, we're going to work with dedicated models to really solve and really nail down that particular problem. So it's a completely different point of view. On the bright side, these models are going to be fairly small in the number of parameters by today's standards. Okay, so this is the problem that I'm mostly interested in these days. And this is the 3D incompressible Euler and the 3D incompressible Navier-Stokes equations, depending on whether you put that Laplacian term in red or not. If you put it, I would talk about Navier-Stokes. If you don't, then I will be talking about 3D Euler. So U is a vector in R3, which is the velocity of the fluid. P is the pressure, and the initial condition, U is divergence free. And the initial condition is going to be given by this initial velocity, U0. The question that we're interested in is whether from smooth initial data, finite energy, can one find a finite time singularity for that particular initial data? Okay. We believe that the answer may be yes to this question. This is a very long-standing open problem, more than 200 years ago. But lately, in the fluid mechanics community, there have been an emergence of results weakening a little bit these assumptions of the open problem that I wrote down. Okay, so there's the work of Elguindi and Chen and Hao, where they constructed non-smooth initial data, but the degree of non-smoothness is not very high. So it's smooth, but not very smooth. And then subsequent work by Cordova, Martinez-Foroa, and Zheng, where they also constructed a different non-smooth scenario, which is non-self-similar. I will explain what the word self-similar means in 2 slides. Another remarkable result is the one first by the numerical simulations of Guo Luo and Tom Hao in 2014, where they first did numerical simulations for this type of equations for Euler in the presence of a cylindrical boundary. The equations here are put, in principle, on the whole space or on the torus in 3 dimensions. In the case of Luo and Hao, they did numerical simulations inside a periodic cylinder. And then 10 years after the simulations, Chen and Hao provided a computer-assisted proof of this numerical scenario. So the dream is to prove finite time blow-up without any cylindrical boundary using a combination of machine learning, computer-assisted proofs, and classical analysis. Okay, this is sort of the direction where we want to go. And this is the direction that we are aiming for in the upcoming years. Okay, so what are self-similar solutions? I mentioned the word self-similar before. Maybe an image is worth 1,000 words. This is a numerical simulation of something called the Berger's equation. And one can see that the shock forms in finite time. So the derivative of the function will blow up in finite time. But now, if I rescale appropriately, according to this red rectangle, what we see is the following. What we see is that thing on the right, the evolution of the blue curve going towards the yellow curve. So the blue curve is the rescale version of the blue curve on the left. And the nice thing of working on the right-hand coordinates is that everything is smooth here. Nothing blows up. Everything converges to some sort of steady state. And for the computer, it's a lot easier to deal with this kind of simulation because nothing will become infinite in finite time if we work with the coordinates on the right. So the first reduction, or the first sort of goal, is to work with the rightmost coordinates. Namely, we're going to postulate that our function little f is of this form for some powers alpha and beta, and try to find a capital F, which is the yellow curve on the right simulation, and those numbers, alpha and beta. The plan is to use this object, this capital F, as a building block of creating finite time singularities when transformed back into the leftmost coordinates. So the goal, we have changed our goal to find some function, little f, that explodes in finite time, either the function or its derivative, into the complete opposite. It's finding some profile, capital F, which is smooth, and it corresponds to a steady solution or to a limiting solution in the coordinates on the right. So now we are hopeful that computers can help us doing this task. Another ingredient that we're going to need is stability. So as I said before, we want to somewhat show some form of convergence to some limiting object. Or if we weaken that a little bit, we want to show that there is a neighborhood in those coordinates that we never leave. Why is this important? Because every single function in this neighborhood, when transported back to the leftmost coordinates, will correspond to a solution that blows up. So if we prove that we cannot leave such a neighborhood, then that's enough to prove that there is a finite time blow up in xt coordinates. So stability is going to become an important ingredient of our job. We're going to take an approximate solution, and we're going to prove that it is stable. This is an idealistic picture because it's linear, and I'm neglecting a lot of things. But in principle, all nonlinear effects or all other errors can and should be incorporated into these arrows that point in. So we're going to treat all the other errors, including the nonlinear effects, as perturbative in this range. So this is more or less how a meta-proof of this finite time singularity scenario could potentially work. So one, find an approximate self-similar solution. Two, understand the linearized operator. And usually, this operator is going to be pretty bad because it's a linearized operator around an approximate self-similar solution that we don't have a lot of control. It doesn't have as much structure as we would like. But nonetheless, we can split it into three terms. One that we know that we can analyze well, another one that corresponds to a finite dimensional matrix, and another one that is going to be relatively compact and small at the end of the day. Show stability. We can afford to show stability modulo finite codimension, and then upgrade all of these steps, 2 and 3, to prove nonlinear stability. One nice thing is that assuming some condition, one can add viscosity as long as in these self-similar coordinates, it's exponentially small. And I will discuss a bit more about that in the next slides. I didn't say anything about which PDE I was solving. So in principle, assuming that the result is true, and assuming that one can find this approximate self-similar solution, all of these could work for a big class of PDE. The plan is to use machine learning, and in particular, I'm going to describe something called physics in 4 neural networks for the first item, and then use a computer-assisted proof for the middle items 2 and 3. But today in this talk, I'm going to be focusing solely or mostly on the first item. That's sort of the plan and the kind of the meta proof for proving blow up for a given PDE. Okay, so what are pins? Pins are essentially a fancy name for describing a neural network and an algorithm of representing a function. So a function here and a minimization. We're going to represent our functions as these compositions of the activation function sigma and the affine function determined by these parameters wi and b, and we're going to do that several times. So at the end of the day, our functions are going to be represented by compositions of hyperbolic tangent, affine, hyperbolic tangent, affine, hyperbolic tangent, affine, and so on. Many times, 6 times in our case. It doesn't really depend that much how many. The whole point is that the representation is extremely nonlinear. And because of this extremely nonlinear representation, it's going to be able to arrive for the same computational cost to approximate better the solutions of our PDE. So in total, we have something of the order of 10 to the 3, 10 to the 4 parameters that we're going to be using to minimize the residual of the equation, plus boundary conditions, and a few other things. This is given by the W's and the B's. So we're going to be using the W's and the B's to optimize the equation residue of the equation. OK, that's the plan. Let me explain a little bit with an example where we can do everything by hand. This is 1D burgers. So 1D burgers, it's great because we can do all of the analysis by hand. It's this implicit burgers. So it's this PDE, ut plus ux is equal to 0. And we're going to assume that u is self-similar. So we are going to be needing to look for capital U and lambda. We're going to be trying to solve equation 1 without the derivative in S term. And we need to solve in both u and lambda. The nice thing is that this is an ODE, and one can solve it implicitly. So one can write, instead of u of y, one can write y of u. And y of u gives us this family of functions given by 2 as a function of lambda. Remember, we wanted a solution that had to be smooth. So this constrains lambda to be of the form 1 over an even integer. Otherwise, we're not going to obtain a solution which is smooth. So the general picture, and this applies to other equations that we have found, is the following. So if lambda is generic, then there is a solution u, but u is non-smooth. That's not a solution that we want, because otherwise we cannot say anything about smooth blow-up. So these lambdas, these generic lambdas, are generically bad. Now, there are exceptional lambdas, lambda n, that give rise, in the case of burgers, it's like this 1 over 2n plus 2, that give rise to smooth profiles. Okay? Those are the good ones. The higher we go in this index n, the more unstable we get. As n grows, the solutions become more and more stable, and then more difficult to find using any sort of numerical method. And our plan is to sort of learn how to use machine learning methods to discover these pairs, lambda n un, for many PDE, even in the case where n is not small, like 0 or 1. So we want to go and find unstable solutions using this kind of paradigm. OK. Let me present another model. This is important because I will explain here the role of viscosity. So this is known as the CCF model, coined by Córdoba, and Fontelos. There is this non-local relation between u and omega, given by the fractional Laplacian. And depending on how much viscosity, how much dissipation we put on the right-hand side, governed by alpha, then we can say different things. So if alpha is small, then there is finite time blow-up. If alpha is big, then there is global existence. Note that between the boundaries of small and big, there is a gap. So people don't know what happens in between 1/2 and 1. This is an open problem. So where is the viscosity going to come into place? Let's go to self-similar coordinates. And then in self-similar coordinates, if we write the PDE, everything is sort of what we expect. But if we look now at the term coming from the dissipation on the right-hand side, there is this factor, 1 plus lambda times alpha minus 1, which is inside the exponential. Now, if that factor is negative, then this is a good exponential, because it will go to 0, as s goes to infinity, and then we can treat that term as an exponentially small forcing. So the constraint for such a proof and such an argument to work is alpha times 1 plus lambda to be smaller than 1. If that's the case, then we win. We can treat this thing as a perturbation, and we can put as much viscosity alpha as 1 over 1 plus lambda. So if one solves the other way around, then lambda needs to be smaller than 1 in order to say anything in the open range where alpha is between 1/2 and 1. OK, so the first solution that we found is given in blue. And unfortunately, that wasn't below 1. Remember, the cutoff to say things in the open range, it needs to be above or below 1. So the solution that we found had a lambda of 1.18. But then, with a lot of effort, we were able to find another unstable solution at lambda 0.6. Okay, so this was the first instance of an unstable solution being found by these methods or by any method for this equation. So this is unstable. There is one non-trivial eigenvalue at mu roughly 0.36. And if we were to prove the existence, we can squeeze a viscosity at roughly 3/5. And more solutions, not just these two, exist sorted by the dimension of the unstable manifold. OK, this is another calculation using machine learning to now find the eigenvalues. We tested it with the explicit eigenvalues that we know that correspond to translations in time and in space and have eigenvalues 0 and 1. We were able to get agreements of order 10 to the minus 5. And then this is the other mysterious eigenvalue that a priori doesn't correspond to a physical symmetry, and that we were also able to find using these kind of techniques too. OK, and after that, we were able to prove the following theorem. Let us take lambda bar, omega bar, be the approximate profile. Then we have a codimension 1 smooth neighborhood of initial data around omega bar, such that it leads to finite time blow-up for dissipative CCF with alpha given by lambda bar, but can be simplified to 3/5. Okay, so that's one application of machine learning into the world of PDE. But you can say, well, it's a 1D problem. Let's see how far you can go. Let me now talk about another, in principle, 2D problem, but this is also a 1D problem as well. This is coming from fluid mechanics. This is the 2D Euler equation in the context of whenever the vorticity is a step function and it's the characteristic function of a set given by this free boundary where the vorticity omega is equal to 1 and 0 outside. So we can write all the dynamics in terms of the free boundary parameterized by this z. And we're going to be looking for solutions at this point, not that they develop finite time singularities, but kind of the opposite. We're going to look for global solutions that rotate with some angular velocity omega. And in the literature, this is known as V states. So this is not new. In the late 70s, Dim and Zabusky were the first ones that did this kind of calculation. Starting from the disk, they were able to bifurcate at the right angular velocity and obtain these non-trivial shapes of solutions that rotate uniformly in time and in space. Now, in '86, Obermann, based on these pictures and other pictures, contemporary pictures, conjectured the following. If you follow the branch of solutions, then at the end of the branch, there will be a singular limiting V state that it will have a 90-degree corner at the tip. You can see that in these cases, like for the 3-fold, 4-fold, 5-fold, and so on, at least to the naked eye, it looks as if that sort of pinching or that sort of corner happens everywhere. There is a slightly similar statement in the case of 2-folds. But up to date, this is an open problem. So 40 years after, no singular V state has been proved to exist. OK, so we're trying to give it a shot. And just a small taste of how the equation looks like. So if we substitute, impose the rotating frame, and try to solve, we need to solve this kind of singular integral operator type of equation, where F1 and F2 are singular integral operators acting on R, which is our unknown, and omega is the other unknown. So we need to solve for this omega RR prime equals some unpleasant singular integral operators. And omega is important because there is only one value of omega for which this works. So we're not the first ones to try, but this is a difficult problem, even numerically. So there are some traditional strategies highlighting the work of Lusato-Fegiz and Williamson, or our own spectral methods with some tricks. But instead of doing it this way, we're going to use machine learning. So there are two, or at least two things to take into account. One, there is only one value of omega for which the problem has a solution. And another one is that we need to make sure that the corner stays put to 90 degrees. We could incorporate this as a loss, as penalizing the fact that we're far from 90 degrees, or into the design of the neural network. So some other important things to keep track of is that the accuracy of the numerical integration of the singular integral operators is important. And we're going to go through a two-stage training, where in the beginning, we're going to avoid local minima. And then later, once we zoom in, then we're going to try to converge much, much faster. So this is a two-stage method, where in the beginning, this is also, we do like stochastic gradient descent. This is why you see all these peaks going up and down because of the stochasticity. And then at the end, once we are close to the minimum, we just try to hit it with a second order method for faster convergence. Okay, so other things that are important. So this is a result with Maria Prat-Colomer, who is my graduate student at Brown. We were able to find the two-fold candidate with fairly good precision. We also did other tricks, like asymptotic analysis, and also taking into account different sampling strategies. For example, standard is not doing any sort of distribution or doing a uniform distribution of sampling points. Logarithmic is sampling more in a logarithmic way towards the tip. And asymptotic is combining that with asymptotic expansions towards the tip. So incorporating mathematical analysis into the picture leads to better performance. And the way one needs to incorporate this mathematical analysis is not so evident. So this is really a challenge when it comes to designing this kind of methods. We get very good performance in terms of like comparisons with the literature, agreeing to 6-digit with the previous best simulations, and we are happy with this kind of results. Let me move on now into 2D problems. Okay, so far there were easy 1D not so easy 1D with all the singular integrals and so on. Now let's move into 2D problems. So let me talk first about Boussinesq. So the 2D Boussinesq equations are given by this system. In this case, we're going to work in the upper half plane. So we have U, theta, and P. And again, we're back into the singularity business. And we want to make these self-similar ansatz and try to solve for the self-similar solutions. We want to get rid of the pressure, because the pressure will induce some nasty non-local behavior, and we will have to invert a Laplacian across many scales. So we're going to work with vorticity formulation, and we're going to work with this omega, which is the curl of the velocity. And in those variables, omega, phi, and psi, the solution and the system is overdetermined, but that's all right. So we are going to impose a certain amount of symmetries, some boundary conditions at infinity, and then we were able to find these kind of self-similar solutions for Boussinesq. So this is our previous result released a couple of years ago, and we were getting fairly good errors back then, 10 to the minus 5, 10 to the minus 4, relative to order 1 or order 10 of the fields, and good comparisons with the available literature at the time. Okay, so this is a result from a couple of years ago. What's the result from this year? So we have been working with DeepMind on improving these benchmarks, and this is sort of the picture, let's say, the literature picture at that stage, where for this CCF model, there was the first calculation by Lushnikov and collaborators, then our calculation of the first unstable solution, and for Boussinesq, there was our calculation of the stable solution. And what we have managed to improve upon is this sort of set of new solutions going really into dimensions of the unstable manifold, where it is not so small anymore. It's sort of, the unstable manifold is of moderate size. And this is important because when it comes to finding solutions of 3D Euler or even 3D Navier-Stokes, it is very conceivable that, that those solutions are going to be unstable. So from the methodological point of view, we are now able to understand how these machine learning methods can allow to compute moderately unstable solutions of a few PDE involving a lot of new discoveries along the way. We are able to improve on our previous accuracies. We now can allow for ultra high accuracy of orders of 10 to the minus 8 to 10 to the minus 15. We use mathematical knowledge of the PDE to design better networks, and this gets us better solutions that somehow gives us more mathematical information of the object that we feed again into the neural network, and this gives better performance and so on. We can also do extrapolation. If we know a few values of the first few unstable, we can get relatively good accurate guesses of the next one. And asymptotics now become crucial in the design of the networks and when it comes to convergence of the methods and faster convergence or even let alone convergence for these highly unstable solutions. So let me stop here. Thank you very much for your attention.
Thank you very much for a fascinating talk. We have time for several questions.
Maybe a naive question, but what's special about the hyperbolic tangent?
Nothing.
Nothing.
Nothing. If you have something that has that sort of sigmoidal shape, that also works. It's more traditional now in the ML literature, like to use hyperbolic tangent, but there is nothing. If you use something that qualitatively looks like that, it also does the job. So there is nothing really particular about that. You need the function to be smooth, because your object that you're looking for is a smooth object. So if you put something which is not smooth, then it doesn't do a good job. But as long as it has that kind of qualitative shape and is a smooth function, you're good to go.
So in some of the algorithms that you mentioned, which were improvement over traditional human algorithms, how do they compare in terms of the simplicity? I mean, for example, when I looked at the first alpha tensor for matrix multiplication, which was an improvement over Strass, and yes, it was an improvement, but it just blew up. It was hard to use sort of thing.
It depends on the problem. So for some problems, one can really distill a simpler way of an algorithm. In some other cases, it's more difficult. So this is somewhat problem dependent. In some cases, you can get very quickly the insight, either through the human. Let's say the human realizes like, oh, there is this pattern, and therefore I can improve, and this is better. You could also ask the LLM for the distillation of that, and that sometimes works. Or sometimes it's just difficult to parse. So we have examples of like all three categories.
Okay. Thank you. Thank you.
I have a question. If you go back to the Boosin-S slide for a minute, I don't know if you can do that.
The one with the picture?
No. Before, the one with the equation.
Okay.
That one. So, so that's basically the Euler incompressible fluid flow equation.
Correct.
And you said you get rid of the pressure.
Yes.
The pressure in that equation is the crucial element of that equation because that's what keeps it incompressible. So when you get rid of the pressure, you change the whole nature of that equation from a non-local to a local equation.
That's correct. When I say I get rid of the pressure, it's not saying that I set the pressure to be 0. I mean it to say, as in I work with a different set of variables, like vorticity formulation, so that numerically I don't need to deal with the pressure in that way. But the pressure is there. What I mean to say is that from this formulation, if I get a solution of this system, then I get a solution of that system at the bottom over there. But it's just for computational purposes that working in this set of variables leads to worse performance.
Well, okay, but the pressure has its own equation involving the Laplacian.
Yeah.
And I don't see that in that secondary set of equations. That's what the...
You can go, if you solve this equation here, you can go from these variables using the Biot-Savart law and return into this set of variables. It's just that in order to solve, instead of trying to solve this system here, we try to solve this system here. So mathematically, both are equivalent. It's just when it comes to feed the system into the neural network, this system seems to be more advantageous.
And you say the equations are local there. Do you
Yes.
see that? But they're not local because they're non-local because the pressure involves the entire system.
If we were to go to this set of variables.
Okay.
So solving these equations is a local problem, but if I were to go back and express my solutions from the second system as solutions of this system, then that would be the non-local part.
Okay.
Yeah, I have a naive question. So like in the beginning, talking about AI or like the machine learning, so I want to know like when AI is further developed, let's say after 5 or 10 years, so by then, in your opinion, like what's the main role of mathematician in mathematical research?
Oh, they will come. We will come with better questions. We will be able to do deeper problems. This is what I think that mathematicians will do, because we will have more capability of solving problems. So we won't run out of problems to solve. We will just come up with harder problems, deeper questions, maybe more interesting, I don't know. But I think the role of mathematicians is not going to be just be the slave of the AI, but just we will come up with better methods or other more intriguing questions. Think of it as, for example, before the computer era, the type of questions that mathematicians would solve or would be able to solve was far different than after the computer era. So I see this as sort of a similar phenomenon. We'll have more ability to do stuff.
So fascinating indeed. So the training problem is in principle is non-convex, which means that the loss function in principle could admit multiple local minima.
Absolutely, yeah, this is a real issue.
So have you seen some evidence for the presence of multiple local minima?
Oh yeah, absolutely. Every time the thing, I'm showing you the simulation that went well, but there are 999 that didn't go well. So any of those 999 is stuck, or well, some of them are stuck at a local minima.
Okay.
But yeah, no, definitely. This is what it makes the minimization problem challenging, because you occasionally, well, it depends how you program it, but you may very well get stuck into local minima, absolutely.
So is there any way of showing that the minima that you did find are in fact global?
No, I don't know how to do that. I wish, but I don't know.
Thanks.
I mean, you can use it a posteriori to produce a proof out of the candidate you find. But from the description of like the object itself, I don't know how to do it. I can answer your question by then like providing a full proof of the existence of the object, blah, 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 but not at the level of properties of the minimizer.
Yeah, no, that makes sense. Thank you so much.
All right, so we got maybe one more question here.
Professor, so the equations that we have got, I see that you have solved using the physics-informed neural network.
Mm-hmm.
So have you compared the results with some numerical method? Because in my experience so far, I have seen in 1 or 2 dimension, numerical methods perform much better than the pins. And as the dimension increases, the pins like take over.
So it depends. The important keyword here is discovery. None of these solutions that I'm reporting are guaranteed to exist. So if you have that piece of knowledge that you are convinced and you know that such a solution exists, then I agree with you. Then in fact, any method, quote unquote, could work. But if you don't know whether these objects exist, this is where I have found the power of neural network to be the largest, as in telling you that, well, you should look into this region of parameter space. And this, I mean, I've tried multiple times with many methods, and they never work. So it is very important here to have this additional knowledge that there is a solution. So that really makes a difference. And then if you have it or if you don't have it, makes the comparison very, I don't know, difficult or very different.
So, Professor, in the end, using pins, here we are finding something that is like a solution.
Correct.
Thank you.
Yeah, all of these are, I didn't claim any, well, I claimed one theorem, but all of this is to be able to find numerical candidates from which to build a mathematical theorem of existence of whatever object. This is all in the context of the first step of the program that I outlined. And there is absolutely no need to do it using machine learning. For us, this is the way that works better, but in the context of the full proof, it doesn't matter how you find this approximate solution. So I'm not trying to defend like pins or anything. This is just something that worked for us, but it may or may not work depending on the problem, depending on the equation, depending on the dimension, and so on. This is what we are using as part of our first step of this sort of long-term program. But again, there is nothing that sort of says, oh, pins are so much better than any other technique. I'm absolutely not claiming that.
All right, well, thank you for your lovely talk.